Let's do. Okay. Some recap, whatever we studied in last class. Chapter is all about AC. So the current, instantaneous current at any time is given by I naught sine omega t, right? And the instantaneous EMF or voltage at any time is given by V naught sine omega t, where I naught and V naught are the peak value or the amplitude of the signal. Then we also learned about something called average value. Average value of I at t. Average value of I at t is given by 2 I naught by pi, which is coming up to how much? 0.6877, right? 6877. 637. 0.637, sorry, 637 I naught. And similarly, the average value of V at t, which is average value, which we will say as V average, is given by 2 V naught divided by pi, which is 0.637 I naught. These two things we have studied. And whenever you are calculating average of any function, we also studied average of a function, say f of t, is calculated by integrating it from 0 to t, f of t dt divided by the whole time 0 to t dt. And when we calculate average for a signal, when we calculate average, we are always taking half cycle. Till this much we had done, right, in our last class. So today what we will be focusing upon, the next parameter, which is called the RMS value. So we'll see the derivation of RMS value, how we get the RMS value, and then slowly we will be getting inside. This is all we have done, right? So this is all we have done, right? Our discussion today is and this also we have given you an idea. RMS stands for root mean square. Root mean square. Okay. So some of the notations that you should know, like if you see the signal of voltage as V at t equal to V naught sine omega t, there are a lot of signals out here in what do you call symbols out here. V naught stands for peak value. V naught stands for peak value. V average stands for stands for average value. And when we write as V will stand for V RMS value. We are not started. So root mean square we will be doing today. We'll see the derivation of this. But these are symbols that you should know. Like when you see an appliance, there it will be written V equal to 240 volts. So they are actually referring to RMS value. In this whole world, any measurement of alternating current is RMS value, RMS value, RMS value. Whether they say I, similarly I, if you write I means I RMS, the root mean square value. Okay? So root, mean and square. So we'll do our derivation. So we are trying to find out the I RMS. So I RMS will be given by, first we will take I at t as a function, square it up, right? Root mean square. Now we have to do the mean of this. So mean of this is given by 0 to t divided by 0 to t dt, and then root. Then we'll do the root of this. Is this understood? This is what is known as your RMS value. So we are going to calculate, we're going to derive this right now and see whether what is the expression that we obtain. Okay? इसको हमें करना है. So we'll break it up into all small parts. We'll first take the numerator as usual. So let's begin our derivation from the numerator. Let's start with numerator. My numerator is 0 to t I at t whole square. All right, this is my numerator. So the numerator will become 0 to t I naught square sine square omega t, which is I naught square can come outside, 0 to t sine square omega t, right? Now the other day I had shown you, so I'll not spend that much time again. Sine square theta is equal to 1 minus cos 2 theta divided by 2. You need to know this identity. This is number one that we will need to know. The other thing that we need to know here is, now when we are doing this, what you call a root mean square, we are doing this root mean square over the entire cycle. So we are doing over entire cycle. So we take omega is equal to 2 pi f, which can be taken as 2 pi by t. That means t's value this time will be equal to, t will be equal to 2 pi by omega. Previously, it was equal to pi by omega. Now it will be 2 pi by omega. So let's do our numerator. Our numerator will be I naught square 0 to 2 pi by omega 1 minus cos 2 omega t by 2 dt. Is this much understood? 1 minus cos 2 theta. Okay. So let's go more simpler. I'm just trying to save space, so I'm making it smaller and smaller. Okay, if you're fine with this much, so I've made it smaller. So now what do? We take our I naught square and I open a second bracket. All right, and I naught square, I can take the 2 also outside. So I've taken the 2 outside. I have an integral 2 pi by omega, and here it will be what? 1 dt. So I can write this as dt. Okay, so far. And then I have integral again 0 to 2 omega cos 2 omega t dt. My second bracket closes. Fine. This can be now further deduced as I naught square by 2. All right, dt's integral will be t, and t is from 0 to 2 pi by omega. Fine. And here it will be minus sine omega t by 2, 0 to 2 pi by omega. This much. Okay. So if I look at this thing, this will be I naught square by 2, 2 pi by omega minus 0. This is the first limit reduced. And minus, I'm taking the half outside, sine omega into 2 pi by omega minus everything multiplied is sine 0. Perfect. Till here, no issues. Okay. So this becomes I naught square by 2. If you see inside, this will be 2 pi by omega, right? Minus 0 is 0. Okay. Have your attention out here. Omega cancels omega. Sine 0 is 0. Sine 0's value is how much, beta? 0. And sine 2 pi is also 0. So half into all these things now become 0. So what do we have? We just have this thing, right? Out of which I can further take off what? I can take off 2 and 2, right? I can take off this 2, I can take off this 2. So my numerator is ending at pi I naught square divided by omega. This is my numerator. Okay? This is the numerator. Okay, let's see our denominator. Let's see the denominator. So my denominator is integral 0 to t dt, which I can write as 0 to 2 pi by omega dt, which comes as t, and 0 to 2 pi by omega. So this will be ultimately 2 pi by omega minus 0, which is finally equal to 2 pi by omega. Right? Now we need to find the value of IRMS. IRMS is root under numerator by denominator. Okay. So let's take the numerator. The numerator is pi I naught square by omega into denominator. What is the denominator? Divided by this. So this can be omega divided by 2 pi and root of this. Dekho to beta. Have you understood this? numerator divided by denominator. So here also some interesting things happen. Omega goes, pi and pi goes. So we come to our IRMS value, which is very, very important for you. This will always be written as I. You know, in grade 10, when you used to do a heater consumes current I, that was IRMS all. So IRMS I is given by I naught square will become how much? Root I naught. And 2 will become root 2. This is equal to 0.707 I naught. So the RMS value is always 0.707 of I naught. Similarly, the VRMS will always be 0.707 of I naught. V naught, sorry, not I naught, V naught. 1 upon root 2 is 0.707. Is this thing understood? Can I change the screen now? So let's now see it in this manner. Let's take a plot and understand what all parameters are important for us in AC, right? So I'm taking, say, I'll take a current plot only. So yeah. So these are my, this is say 0. I'm seeing it from angle perspective 0. And then I have pi by 2, pi, 3 pi by 2, 2 pi. Okay. This can also represent your time. Okay. It's the same as the time axis. So this is pi by 2, pi, 3 pi by 2, and this is 2 pi. Our signal is, we will just see from current. So these are our maximum members. So this is minus I naught. This is plus I naught. Okay. So how will your sinusoidal signal look like? So you will take a peak value here, and then again the minimum value here, right? This is my curve of, this represents I at any time t, instantaneous current, I naught sine omega t, right? And this omega t, this part which we will study today, this omega t is actually known as the phase. We'll learn what is phase. This is known as the phase, omega t, right? Now, what all other things did you study? You studied, one was I average. I average is 0.6, how much? 637, right? 0.637 of I naught. 0.637 of I naught. That means, let's make its demarcation. 0.5 of I naught is here. So 0.637 means somewhere here, little bit more than, right? So this is your average, I average on the negative cycle and on the top cycle. Did you understand? This is I average, IAVG, which is equal to how much? 0.637 I naught. And then we also need to have some, so you'll get a fair bit of idea what actually we study here. And then we also need the RMS value, which is of more importance, but that's 0.707. So a little bit higher than this. right? And somewhere here. Okay, so this is this is my, this is IRMS, also write as I, which is 0.707 I naught. This is also IRMS negative. Okay. Similarly, if it was a voltage signal, same would have come for voltage. So what is important for us so far that we have studied? Whenever we in AC current, we have something called instantaneous current. Then one, we have got peak value of the current. 3, we have got average value of the current, which is given by 2 I naught by pi. Remember, it's 2 I naught by pi only when your signal is I naught sine omega t. And then you have a IRMS, which we write as I. And this is given as 0.707 I naught, or which is also equal to I naught by root 2. Now let us understand what all these mean for us. Okay, so right now, let's say the voltage at my house is right now 220 volt AC. This is how it will be written. The voltage entering that particular monitor or the fan is 220 volt AC, right? So let's understand 220 volt, but the voltage is coming in a sinusoidal manner. So what does this mean? This means this is the RMS value. That means right now the voltage is 220 volt. This is plus and this is minus 220 volt. This is what the measuring device is measuring. If I put a voltmeter, it's going to measure this. Then there comes something called peak value. There has to be a peak value also. So when you go for peak value, it will be root 2 times of this. So 1.414 multiplied by 220. So my peak value of the current is 311. So this is plus 311 volt minus 311 volt. So what you should understand is, if you touch the live wire, it's not that you are getting a voltage of only 220. 220 is what is stamped. Once during the time, you will get a peak voltage of how much? 311 will enter your body. Is that understood? Okay. And average, obviously, you know, if you want to find out. So this is VRMS. V naught will be equal to how much? So this is on voltage scale. Huh? Please don't get confused. These are voltage values. Okay. These are voltage values. I have done them on same curve, so it is easy to say by voltage. So V naught has come to 311 volt plus minus. V RMS is this much, and V average, if you want to find V average, it is 0.637 multiplied by 220. So that gives me, the average is around 4.637 multiplied by 220. So the average is 140.14 volt. Okay. So if a person, as you say that, let's say from current perspective, my iron is pulling 1 ampere AC, then what is this 1 ampere? This 1 ampere is IRMS. Any measuring device always measures the RMS value. Then they will tell you, because the current is also consumed by your, what do you call, iron in this manner. It's not a steady current. So they will ask you, what is the peak value? So you will say 1.414 multiplied by, say, 1 ampere. So it will be 1.414 is your peak value of the current. Okay. So we should also define in this case, what is RMS current? What do you mean by VRMS and IRMS? IRMS is the steady current. IRMS stands for the steady current. And it is the steady current which will allow the same amount of charge to pass through, over the same time interval as an alternating current of I naught sine omega t would pass for the same period. See, this is just a generic measurement. How do you measure? What is the way to relate? What is the way to relate between IRMS and instantaneous current. So the RMS current is a steady value. That means this is like a direct current. So the RMS current is the direct current which will push the same amount of charge over the same interval of time as a alternating current would push with the signal I at t equal to I0 sin omega t. The alternating current amount of charge it will push is same as the RMS will push. And average would push over half the cycle. Average pushes half the cycle, RMS pushes over throughout the cycle. Okay? Is this understood? Okay. So first list of formulas you can keep noted, which you will be needing. We'll do when we do our numericals. So keep some these formulas. Average is equal to 2 I naught by pi. RMS is equal to I naught by root 2. I naught is the peak value. So if somebody says, say for example, somebody says the instantaneous current is given by 5.4 sin omega t. Can you calculate all values? I can help you with a calculator. What does 5.4 stand for? Peak value. I naught. This divided by root 2 will give me RMS value. And this multiplied by 2 and divided by pi will give me average value of the current. Okay? Chaliye. Our next concept for the day is to understand a concept called phasor. If you understand this much, then all RLC circuit will be clear for you. Phasors. Now, neither voltage nor current are vectors, but a phasor diagram, what we draw is a phasor diagram. A phasor diagram is the diagram of a rotating vector. A phasor diagram is a diagram of a rotating vector, and for our this chapter we assume voltage and current in form of phasors. I can't use the word I assume them as vectors because they are not vectors. So I assume them in the form of what? Phasors. What is a phasor? A phasor is a rotating vector. So let's see. So and this will take some iteration. So you first observe how the diagram gets made. So and then only start making any iterations over it. Okay. So let's see the phasor diagram. Immediately don't make anything because there may be some iterations. So first try and understand. Chalo. Phasor is a rotating vector. This is my typical, any vector will rotate always in anti-clockwise manner. From 0 degree it will start rotate. So let me make one particular phasor out here. Okay, let the phasor be represented by a yellow arrow. This is a phasor. Okay, and we start our phasor and we call this as, say this is the peak value of the current I naught. This is the peak value of the current I naught, and this is a phasor which is rotating. Okay, while rotating, this is rotational motion. As you know, displacement, angular displacement is equal to angular speed into time, right? Theta is equal to omega t. So I call this angle as how much? This angle is omega t. Is this much understood or not? Right? Now, the signal that I am taking for my AC current is I naught sin omega t. This is I naught, this is I naught sin omega t. So what is I naught sin omega t? I naught sin omega t is the vertical projection of this vector. Very easy. I'll just mutate it for once, you will understand. What is sine of omega t? Opposite side by hypotenuse. The opposite side can be this side also. This is also the opposite side. So what is the opposite side equal to? Hypotenuse multiplied by this. What is your hypotenuse? I naught sin omega t. Is this clear? So if it's not clear, tell me, I can explain again. Is this, have you understood? You want to know it once again? Okay. imagine a triangle out here like this, right? Okay, tell me, what is sine of omega t? What is sine of omega t? Sine of omega t will be tick divided by I naught. Do you agree or not? So what is tick equal to? I naught sine omega t. That's basically this. Have you understood? That's the instantaneous time. So if I take the vertical projection, then I get instantaneous current. If I take horizontal projection, then I get I naught cos omega t. ठीक है? So let's take the vertical projection of this. एकदम घबराओ मत, tension मत लो. So let's take the vertical projection, right? And then what is this? This is I at t. I at t. I naught is a fixed value. Do you agree? So I naught is the radius of the circle. So when it comes here, what is the angle it will make? Pi by 2. Pi by 2 is sine 90. Sine 90 is 1. At that time, instantaneous will be equal to I naught. See, I at t. Okay. Look at this this vector I at t. I naught is fixed beta, but I at t's size can grow and become small or big. Do you understand? When you are coming here, this itself is the I naught, I at t. When you are here, then I at t increases. Again, when you come here, I at t will slowly decrease. And here it will again become 0. There is no vertical projection. Have we understood this or not? Okay. Now, what I do, I now take these projections out here. All right. Now, similarly, when omega t is equal to pi by 2, when omega t is equal to pi by 2, there can be something like this. Omega t is equal to 0 or pi, the central line works very fine for me. Then 3 pi by 2. This is something. Agreed? And then in between also, if you wish, we can take something in between also. When it is at between, at that time, I don't know what is the value. At that time, at least I will say it is this phasor has come here. The phasor has rotated and has come here now. Okay? And this is still I naught, no doubt about that. But right now, this will be known as my I at t. Is this understood or not? I at some instance of time t. And this is my how t is going. T you can, or if you get confused, this, let's say that's the angle, and we can see t on this part also. So let's find out. So when you are at 0, so this is your 0 degree, this is your pi by 2, this is your 3 pi by 2, and this is your, sorry, this is your pi, this is your pi, this is 3 pi by 2, and you are back to 2 pi. Agreed or not? Let me make those equal divisions here also. Say this is pi by 2, pi, 3 pi by 2, and 2 pi. Clear? And for our benefit purpose, we are keeping a time axis also right at the bottom. Don't get confused about it. Actually, this itself is time and both displacement, but this is my time axis. Just for your interest purpose, I have kept a time axis out here. Okay? So now how does it plot? I equal to I naught sine. So this phasor is rotating. For here, when it is here at 0, so let's put some points. At 0, it is at 0. Correct? When you are coming here, it must have come out here. Then at this peak, it takes here. Then it will rotate on this side, similar, will come here. Then it will come exactly out here. So, no, not that. Then it will come somewhere here. And then it will come to again a 0. And then, obviously, take this, and then it will take your this value. So let's put our values. So this is 0, this is pi by 2. This is the linear impression of the waveform. Which one? Let's see, this will go here, 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 pi by 2, pi, 3 pi by 2, and 2 pi. Oh, that particular dot, yeah. This dot should come at the bottom. That's what you're trying to say, right? Yeah, this dot will come here. Correct. This dot will come here. Which one? And 2 pi will be 0. Sorry, huh? Correct. Thank you. 2 pi will be 0. So this is our observation of the waveform. This is how the waveform of this particular thing called I naught is behaving, right? So let's complete the wave. Let's complete the wave now. So I'll get a wave like this. And this is the waveform of this is a current waveform of the phasor diagram, how the current is moving, right? But if you look at voltage value is always more. In last class also we saw the value of voltage is more. So if I try to plot voltage, then how it will be? Just 1 minute. So say I take a voltage circle, which is a green circle. Okay, sorry. So one minute, children. So my voltage diagram will be right. And now you can plot a voltage phasor also, your wish. So this is I naught. At that same time, the voltage will have a bigger one. Okay, and say we are on the same phase. What are we trying to do here? We are saying that the voltage is V at any time t is equal to V naught sine omega t. So you just have a look on the phase. This is also omega t, this is also omega t. Okay, so that means they are on the same phase. Same phase means, try and understand, the overall length of the phasor will tell you the magnitude of I naught. Now if you do it in graph paper, say you take a current of 5 amperes and you say 5 amperes equal to 5 cm and you do it on graph paper, it will exactly come similar. But my current, for the same signal of voltage and current, the current value is always less than the voltage numerically. So the voltage phasor will be a bigger diagram. Have you understood? Both are having omega t as their phase. How to understand? It's a parade where there is a short height soldier and a taller soldier marching together. But their hands and cufflinks will move at the same time. Got it? The taller soldier will also take his hand up. His hand will reach a farther distance. The shorter soldier's hand will reach a lesser distance, but the hands will go up at the same time. So now, so if you enjoy this little bit more, then I would take the vertical projection. Say, I would take the vertical projection here, and in this case, this one would be my. This one would be my. This would be the voltage V at t, instantaneous voltage. This is V at t, because this is V naught. This violet is V naught. Its projection will be V at t. Have you understood? Right? And if I just remove this t, and let's say I plot one more vertical line from here, right? The same phase means, and I'm giving my voltage signal with this violet color itself. So how will the voltage signal go? The voltage signal will go like this. See, at the same time, right? So it has to cross through some point here. So it will go like this, come like this, come here, and just that the amplitude of the voltage signal is more. This is V at any time t is equal to V naught sine omega t, and this is I at any time t is equal to I naught sine omega t. Have you understood this or not? This behavior will be seen only in a resistive circuit. We will get into a resistive circuit, but keep this in mind. If your AC circuit has a load which is only a pure resistor, right? If you remember, we saw in the earlier class, like suppose you have a resistor R, then what do you say? V is equal to IR, beta. We can write this. So what is the value of I? I is always equal to V upon R. So what is the value of V? V naught sine omega t, and this is R. This V naught by R is known as I naught sine omega t. So this is I at any time t. So if you see, the phase difference is 0 between the two, and this happens only in a pure resistive circuit. But when we go to capacitive circuit, as we will be going now, and we go to what you call inductive circuit, we will see there is a lead and a lag which will happen. There will be a lag and a lead happening out here. If the voltage takes a cos omega t, the current will be taking a sine, or vice versa, and that will come up in the next discussion. So just take this. If you have understood this diagram, very good. If you have not understood, if you have any doubt, you can ask. This is a combined phasor diagram for both voltage and current. Voltage being shown by the yellow one, current being shown by the yellow one, voltage is being shown by the violet one. Nobody will ask you any question from this. Your understanding should improve when I take up the next part of what is happening in an inductive circuit. At that time, when I tell you lead or lag, right? So she has asked a nice question. Let me tell you one thing. Current phasor is here, voltage phasor is also here. Agreed? Does current lead voltage? No. Both are at the same time. They may be shorter soldier and taller soldier. If I tell you current lags by 90 degree, that means when voltage will be here, current will be at 90 degree out here. And if I tell you current leads, when voltage will be here, current will be 90 degree apart from here. So at that time, this similarity of graph over each point you won't find. And what is lead and lag? Just imagine, this is sine omega t. Lead means sine omega t plus pi by 2. Sine something plus 90. So it comes to Bahubali line. Function changes. It becomes what? Cos omega t. And a cos function will not start from here. The cos function will be starting from negative pi by 2. वो आगे lead कर जाएगा. Before the voltage comes, the current is already passed. So you should ask, sir, in our house, what is happening? In our house, neither we have a pure inductive circuit, nor we have a pure capacitive circuit or a pure resistor. So what is the equation there? Is it sine omega t? I would say no, beta, it's not sine omega t. It's sine omega t till the plug point. Then you have connected, say, a microwave. Now inside the microwave, what is running? I would say the microwave is a resistor, it's a capacitor, it's a RLC circuit. I would say it's a sine omega t plus some phi. Not 90 degree. Not 90, plus some phi. Phi is the phase difference. Did you get it? A phase difference between two children performing a group dance will not show. There will be an error, but the error will not be something to ridicule about. It's just like kiddos. When 5 children put their hands up, that child will be putting the hand down. So that's a phase difference of up and down. But suppose the phase difference is like this. When I put my hand up, you are putting it till this much. If this is constant, then there will be an orchestrated rhythm you will see. But for everyone, if the phase difference changes, I am putting my hand up, she's putting this much, this fellow is putting this much, then we say, hey, koi talmel hi nahi hai isme. So when she plays a guitar to a note, to a song, and I am playing the synthesizer, we cannot have a phase difference. We are playing to the same song on the same scale. What is different is her amplitude might be different, but the guitar is sounding more. It has to be like this. But if there is a lead or lag, then her face will become like, what is this doing? जिसको हम हिंदी में बोलते कट गया है ताल. You know, he's out of rhythm. So that will be out of rhythm. And in inductive and this thing, it will be out of rhythm. So this is very interesting. Phasor diagrams we use for, it's not for electricity only. You can use this for any simple harmonic motion. You can use this for acoustics, measurement, whatever, just to give you a wavefrom, because these two poor fellows are not vectors. But to imagine them as vectors, we can't call them as vectors. We give the phasor impression on them, and we try to study how their propagation happens. Is this understood? Can we go now to our pure resistive circuit? Aye. Let's go to a pure AC resistive circuit, or we'll change the word, AC circuit with a pure resistor. Okay, we say AC circuit with a pure resistor means the load this time that I have is just a pure resistor and nothing apart from that, So my circuit is so I have a AC circuit now. Okay, I will not put any direction of current like I used to put in DC circuit, because here current doesn't have a direction. Current is oscillating at what? 50 hertz, right? So I call this as an AC circuit, which is actually giving you an EMF where the EMF condition is V at t is equal to V naught sine omega t, and this circuit has a pure only a resistance which is given by R. And I'm interested in finding out what beta? I'm interested in finding out what is the I, instantaneous current. So the instantaneous current I, V by I equal to R. So I equal to V at t upon R. This is from Ohm's law. Okay? So how much do you get? V naught sine omega t divided by R, and this quantity is known as I naught sine omega t. So children, what you should write now here is, you write that in a pure resistive circuit, the voltage and the current do not have any phase difference. They are on the same phase. So in a pure resistive AC circuit, voltage and current are in same phase. And I would not like to use the word voltage and current, instantaneous voltage and instantaneous current. Have you understood? So such a circuit, if somebody gives you and tells you calculate the value of V, what is V, children? V RMS. Will you not be able to calculate? You will say V naught upon root 2. Calculate what is V average. V average will be how much? V naught 2 divided by pi. Okay? And these will also obey all your rules. So here we also calculate, say, power, average power of the circuit, which is also denoted by P bar, average power. Now you think power is equal to what? I square R. So you might say, sir, how can the power should be 0? Because the current overall in a cycle, what happens? The current is actually making a positive cycle as well as a negative cycle, but it is I square. So all the negatives will go away, right? So the power will be given by, my average power is, so this is I at t square into R. Clear? Okay. And so when you calculate the average, if you calculate the average, it won't, I'm sorry, I should not write it this way. Yeah, even this is fine. So average power is equal to 1 minute. 1 minute, children. To get your confusion through, we'll not write average power first. So let us write instantaneous power. instantaneous power, which is given by power at any time t, will be given by instantaneous current square, right, into the resistance I square R. Clear? Now, if you want to find out average power, then what do you do? Average power means you have to again integrate 0 to t p of t divided by 0 to t dt. Ultimately, if you do all these things, if you that will come again same as you will be having the equation of sine square omega t, and sine square in your text, in your NCERT book they will always write 0 to t sine square omega t is always equal to half, and that you have also proved, because in this case sine square means you will go for the full cycle, so this will be 2 pi by omega sine square omega t. This will be half. You can yourself do. This will be 1 minus cos, and the half will be outside. ये half हो जाता है, ठीक है ना? So this average power is actually your P bar. But when you finally calculate, instantaneous power and average power will be same. So sorry, RMS power, this will be given by I square multiplied by R, which will be also equal to VI. You want to see this now in average definition? If you want to see this in average definition, let's see this in average definition. Okay, what is I, children? I is I RMS. I RMS means how much? I naught by root 2 whole square multiplied by R, right? But we want to see this in I average value. Okay, so I naught by over L means I naught square root 2 becomes half and R. So in your book, average power will be written like this also, the same thing. RMS power and average power will come same. But when you are using average power by this, if you are using half, mind you, then you use I naught. This formula we don't use that much. We will be using this formula only. But keep one thing in mind. Whenever you are seeing the letter alone, it is always RMS, RMS, RMS value. ये समझ में आया? It will be RMS value. Shall we see a pure capacitive circuit now? So in pure resistive, what did you understand? Phase is same, calculation is very easy, everything is like grade 10. So let's go to a pure capacitive circuit. जितना हो सके करेंगे, right? So replace the resistor and make a capacitor. So let's just build the circuit first. Replace the resistor and put a capacitor. Capacitance, and the capacitance is what's C is equal to Q by V, Q equal to CV. You remember this, right? Chalen then, okay. Okay, can I write Q is equal to CV? Our job is to find out what is the current in it. This is a pure capacitor AC circuit. So let's do Q equal to CV. So Q can be written as C. V means the voltage, V at any time t. The current. Wait. Let's say the instantaneous charge at any time will be given by capacitance is constant multiplied by the instantaneous voltage. We are on AC right now. Okay? So I can write Q at any time t will be given by C V naught sine omega t. Bacha, is this clear or not? I want to find current. Current is what? Rate of flow of charge. So we differentiate both sides with respect to dt. Differentiate both sides with respect to dt. Possible, na? So if you do dqt by t, what do you get? You get instantaneous current I at t. This will be given by CV naught. CV naught is known to me. Okay. And omega will come out, right? And rather than that, let me write it like this. I am writing it as C omega V naught cos omega t. देखो बच्चा, C V naught cos omega t. Agreed? Okay. Can I write this as I at t is equal to omega C V naught cos omega t. V naught cos omega t. Are you seeing the difference which has come? The current is now at a cos, right? Now, yeah, we have a habit of writing V is equal to IR. We have this habit of writing where we have always expressed I as a form of voltage upon resistance. Always, whether it is in DC. And right now, just in the previous section, you actually found out I at t is equal to V naught by R sine omega t. This was in pure resistive, pure R AC circuit. Was this not there? So we have a habit of expressing current always with a resistance in the denominator. Do you agree? We need to have that format here also. So I make it at I at t. Can I write this as, I'm writing this as V naught, right? And on bottom, I'm writing 1 by omega C. And then I write cos omega t. Can I write this? Okay, I can write this. This 1 by omega C is actually known as a quantity called Xc. Xc stands for capacitive reactance. Capacitive reactance. Achha, what does this mean? Are bhai, a resistor resists. A capacitor will also give some sort of a resistance, right? This is capacitive reactance, means the resistance offered by a capacitor. This is just a resistance offered by a capacitor. Resistance offered by a capacitor. Maybe you are still not agreeing with me. How can this be resistance? Let's do a check. 1 by omega multiplied by C. Let's do a unit check, right? What is 1 by omega beta? Omega is frequency, seconds minus 1. That means 1 by omega should be second. Do you agree or not? C is equal to what beta? C is equal to Q by V. C is equal to Q by V. That means 1 by C is equal to V by Q. V by Q. Got it? This can be written as V divided by Q divided by S. Q by S is nothing but current, charge upon time. Is this not equal to ohm? Yes. This quantity is resistance. In fact, in AC circuits, right, giving you a very nice example. So an LED glows at 3 volts. If you connect the LED on this plug board, the LED will blast off immediately because you are supplying 200. How much is the peak voltage coming? 311 volts. So we need to put one resistor. And say suppose you don't have a resistor. You can put a capacitor also exactly in that series. The capacitor will behave like a resistor. And how to select the value of the capacitor? Very easy. How much resistance do you want? You should first calculate. That resistance is equal to 1 by omega C. Omega, you know, you are in India, 2 pi 50. And C you don't know. This is how I learned all my electronics like that. See, what I'm trying to say, I want to connect one LED across a 220 volt line. It will blast off. So I need to put one resistor. This resistance is some R. The LED pulls around 25 milliampere current. And I should not go by this. This is RMS. The peak voltage that will come is 311. So I do 311 and 25 milliampere. They will give me the value of R. This R has to be matched by 1 by XC. Sorry, not 1 by XC, XC. Share. Okay, this has to be matched by XC. This has to be matched by XC. And XC is what? 1 by omega C. What is omega if you are in India? 2 pi into 50. Now you know this. You know this value. Can you not calculate the value of capacitor? That same capacitor, instead of this circuit, if you do this circuit, then also your LED will happily glow. And in fact, in all your Diwali lights, have you seen there is a black box right at the start of the Diwali light series, or a white dabba? Yeah. That white dabba actually uses this circuit only. This is called a low current. This cannot take a peak current. For any low current devices like Diwali lights and all, this is fine. It's a very cheap way of making an LED glow using a capacitor. The capacitor will behave like a resistor in this case. Right. So we come back here. Now it's still not done. So I can write my equation I at t is equal to V0 by XC cos omega t. Yes. Now I'm getting a feel of voltage upon resistance. That feeling is coming or not? Yes. So I replace this with I0 cos omega t. Wow. I started with a signal V0 sin omega t, and the current, oh, I can't put that direction. The current at any time in a pure capacitive circuit is I0 cos omega t. Cos omega t. So let's change this and make it a little bit more stylish for you to understand whether it is leading or lagging. I can write this as I0 sin of pi by 2 plus omega t. Sin pi by 2 plus theta. Sin pi by 2 plus theta. This is pi by 2. All sin tan cos. Pi by 2 plus theta means I am on second quadrant and I am on standing line, which is Bahubali line. So he will alter the function. So sin gets altered to cos omega t, and parent function was sin. Sin is positive out here. So this is positive. The idea of writing this for you is that if you see that the input voltage is V0 sin omega t, the current running in the circuit will be I0 sin omega t plus pi by 2. Means here current is leading the voltage with 90 degree. I can write it better now as I0 sin omega t plus pi by 2. Now, this is a pure capacitive circuit. Sir, can we obtain pure capacitive circuit? No, no way you can obtain. No circuit is pure capacitive. But if it was a pure capacitive circuit, then in this case, it is going at 90 degree ahead. Okay? So, if it is going at 90 degree ahead, before these great tenors come, let's see one more thing. Okay? Now, let's see how the waveform will be. Let's quickly do our waveforms. We'll go only by peak value. This is peak current. This is current, peak current, peak current. Voltage will be with yellow color. Okay, peak voltage and peak voltage. All right. So let me plot my voltage. I'll plot the voltage with this. So let's first put pi by 4, sorry, pi by 2, pi, 3 pi by 2, 2 pi. Agreed? And let me increase this little bit on this side also. I'll be needing that. Let me increase it this side or right. And on this also I have put one. Right. So this is 0, pi by 2, pi, then 3 pi by 2, and this is 2 pi. So let's quickly plot the voltage curve. So the voltage curve is shown by yellow. So we'll go by yellow. Voltage is showing sin omega t. Voltage is sin omega t. No doubt. And now we need to show the current. What is the current? The current is cos omega t. That is sine plus pi by 2. Pi by 2 was shown to show you that there is a lead. It's a cos omega t. So how does a cos curve start? So in my typical cos curve, I will put this as negative pi by 2. Have you understood? So the cos curve will start in this manner. When you are at 0, cos will already be at the peak. Cos will already be at the peak. See. Now how to read this graph? See, when I am 0, I means voltage. Current has already taken the peak value. Which one? Current's peak value is less than that. Very nice observation. Very good. Very good. Right. Really appreciate that. So current's peak value is less than that. Yes. I'm not able to match this. Like this it will go. Not exactly matching. When my voltage is at 0, the current is already at its peak. Right? When voltage reaches its peak, current has come back to 0. After this, when voltage comes back to 0, current goes to negative peak. Then voltage comes to negative peak, current goes to 0. So current is always leading. And in inductive, what we will see? Just the ulta. The current will be lagging, the voltage will be leading. Have you understood? So if I denote this graph as I denote this graph as V at a time t is equal to V naught sine omega t, I will denote this graph as I at a time t is equal to I naught cos omega t, or you can write this as I naught sine omega t plus pi by 2. So if you want to study in sine, then please, this is leading. This is a very interesting thing. Have you understood this part? Everywhere we have to show. So you got a pure capacitor. So you write down in this, you write down your note that in a pure capacitive circuit, the current leads the voltage by a phase difference of 90 degree or pi by 2. Current leads the voltage by a phase difference of 90 degree or pi by 2. Understood? And how we got it? Very simple. We put a capacitor, then we put the instantaneous charge, differentiate the instantaneous charge to get the value of the current. And once you get the value of the current, after that, you just need to massage it. Acha, what is important here? You will get a omega c V naught. But you are habituated to always see it as a V naught by something. You have to create that by something. For that by something, you create it as 1 by omega c. And this quantity you call as xc. So in reactance, in inductance, we will have XL, which will be known as, this is capacitive reactance, that will be inductive reactance. The inductor can also behave as a resistor. What is an inductor? A piece of wire which is coiled. So it also is a resistor. You can't stop it from being a resistor. But in inductor, imagine now in our next class how interesting it gets. We'll put an inductor out here. And from here an EMF is going. The EMF is changing the magnetic flux of the inductor. So the inductor by Lenz's law will create another back EMF. Your EMF, back EMF. We apply Kirchhoff's law. And we say that this EMF plus this EMF should be equal to 0. And we won't integrate, differentiate. We will go for an integration. And then we will get the value of what is the instantaneous current. And what we will use, our using will be, what is that? What is the Lenz's current will give you? This will be V naught sine omega t. This will be minus L di by dt. The current is always minus L di by dt. You are giving V naught sine omega t. This fellow is opposing with minus L di by dt. Both oppose, add them both should be equal to 0. Integrate and we will get our difference. Now, and if we see on this diagram, for a capacitive circuit, how it will be? Voltage will be the violet one, yellow will be 90 degree behind it. No, 90 degree ahead of it because the current leads. So 90 degree. In inductor, it will be 90 degree behind. Then you will draw something called an impedance triangle and then you will calculate the values. This chapter is much easier if your concepts are clear. You need not do all those quantization of charge and all.